Okay, welcome back, class. We're going to continue our look at separation of variables today. In the first lesson, I did go through 5 examples with you, and I just wanted to continue here by doing 4 additional examples. These are, again, right from your textbook. I'm working on some of the even numbered problems from exercises 31.2. So here is problem 18. We have ds minus s squared dt is 9 dt. So the whole key to solving these problems is to recognize that we have 2 different variables, and they are s and t. So s here would be the independent variable, while t is the dependent variable. We have 1, 2, 3 terms in example 18. And you can see 3 differentials, ds, dt, dt. So we have to take a look at each term and make sure that beside the differential ds, there is not the variable t. So here's the differential ds, and attached to it, we do not see the variable t. So this is in good shape. But we also have to check that attached or multiplied by the differential dt, we do not have the variable s. So this term is okay because attached to this differential dt, we do not have the variable s. But here's where we have the problem. Attached to this differential dt is the variable s. So we can look to correcting this by dividing all terms by s squared. So would that strategy work? So if I divided this term by s squared, it would just be dt, and that would be fine. If I divide this term by s squared, we would have ds over s squared, and that would be fine. We could integrate that. But if I also divide this term by s squared, I would have 9 over s squared dt. And that then would be a problem term because the variable s would be within this term containing the differential dt. So that's not going to work here. So I'm going to try something different. I'm going to get the terms containing dt on the same side. So I'm going to leave ds here, and then I'm going to move this term to the right side. And of course, when I do that, it will be added. So we're going to have 9 dt here plus s squared dt, like this. And then I'm going to common factor dt from that right side. And now, still I have the variable s in the term containing dt. However, I can now divide both sides of the equation by this binomial. And then I will have ds over 9 plus s squared is equal to dt. So I have fixed the problem because here we do not have the variable s any longer. And in this term, which has the differential ds, we do not have the variable t. So we have correctly separated the variables, and all we have to do now is correctly integrate both sides of this equation. Okay, so when I integrate the right side of the equation here, I'm integrating the number 1, if you like, with respect to time. Well, I'm assuming it's time, but we're integrating the number 1 with respect to t. So that is t, the integral of 1 would be t. And then of course we would have a constant here. Okay, and now on the left side, I want to integrate ds over 9 plus s squared. And you'll find that that is actually here within our table. So we have ds over 9 plus s squared. So if we compare it with this form right here, we have u is equal to s, and the a squared is 9, so a is equal to 3. So we have, so maybe I'll write down the equation that we're using, just really small over here off to the side. So we're using this one, the du over a squared plus u squared. Okay, so that's the equation that we're going to use, and its integral is 1 over a tangent inverse of u over a. Okay, and then of course there's a constant plus c. Ooh. All right, really squeeze that in there. Hopefully that's on the edge of the video. There we go. Okay, so we're gonna use this formula. So we're comparing this with this. And so what we have is the u is equal to s. And a squared is 9, which means that a is 3. So now when we write this down, 1 over a becomes 1 over 3. So we end up with 1 over 3. Tangent inverse u over a becomes s over 3. So tangent inverse s over 3. And the plus c, of course, is all incorporated in the one and only constant here. And then don't forget that we like to clear out fractional coefficients when we can, when we're doing these problems. So that would mean tripling the terms. So I'll call this C1. Now notice when you multiply this by 3, it only affects the constant here. It's not going to affect the argument of the function. So we triple this and we get tangent inverse s over 3. We triple this, so 3 becomes 3t. And we triple c1, so 3c1 would be here, but we would just call that the final constant c. So I'll just put a little note here. Our c is 3 times the original constant c1. Okay, so that's our final equation. So again, in trying to solve the problem for this term, it would not have worked to divide all terms by s squared. That's because this term would then be 9 over s squared stuck to the differential dt. So we will just have moved the problem. So that's why I tried a different strategy. I brought the two terms containing dt to the right side so that I could common factor that differential and divide by the whole binomial. And now we have this term only containing s's, this term only containing t's as required. That's what it means to separate the variables. Okay, let's try this one. This is problem 6 from the same exercises. Now let's take a look at this. We have the variables t and y. Okay, so we can assume here t is the independent variable and y is the dependent variable. So let's see what the issue is with the terms. So there's a problem here already, right? The y cannot be here if the differential is dt. There's also a problem here. The t cannot be here if the differential is dy. And a problem here. The y cannot be in here if the differential is dt. But let's see if we can just solve this using division. So why don't I solve this problem first? So what I'm going to do is divide all three terms by y and see if that fixes the problem. So then this would be t over y dy, and we're dividing this term by y as well, 3t dt, like that. Okay, so my first strategy was I divided all three of these terms by y, and I got this. We still have a problem in this term though, because if the differential is dy, the t cannot stay here. So what if I divide all terms now by t? That's going to give me this, dt over t plus dy over y is 3 dt. So this is what we get if we then divide all terms by t. And I think that fixed the problem. Only t's, only y's, only a constant here. So all terms can now be integrated. Okay, so we've solved the problem. So stuck to the differentials dt, there are no longer y's. And stuck to the differential dy, there is no longer a t. So we're at the step where we can integrate all three of these terms one at a time. What's the integral of dt over t? Right, that's the one right here. It's just the natural logarithm. Okay, so it's the ln of t. What's the integral of dy over y? Also a natural logarithm, the ln of y. What's the integral of the number 3 with respect to t? That's 3t, and then we'll have a plus c. Okay, so the integral of 3 is 3 times t, and that's because the derivative of 3t would be 3. Okay, and that's actually done, except that generally we would combine the logarithms if there are multiple logarithms. When we have addition, the argument is a product, so the argument is t times y. And that's it. That one is now fully solved. Okay, so I'm gonna just put a little box around this formula we used back in the previous question, just trying to keep things a little neater like that. So I hope that you're also copying down notes for yourself in some way, because all of your tests, of course, are going to be open book. And I'd like to suggest that it would be easier for you to access notes on paper during a test than it would be to just have all of the videos at your disposal. Okay, so that's my strong suggestion, that you're copying down the examples as I'm going through them. Or I suppose it would be possible in some way to just get images of these solutions and to print them. Okay, in any case, I'm going to go on to the next problem that I'd like to solve with you, and it is number 16 from your book. Okay, so here we go. This is the question. We have e to the 2x dy plus e to the x dx is 4 dx. So 1, 2, 3 terms again. So all of the examples thus far today have 3 terms. In our last lesson, let's see, were they all the examples? The examples from last day had 2 main terms, 2 non-zero terms. Okay, so here we go. I'm hoping that one term jumps out at you because you recognize that it is a problem. And it should be this one, because here's the variable x in the term containing the differential dy. This term is fine, no y's in there. This one is good, there are no y's in here. This term is the problem. So the variables are x and y, and beside the differential dy, we should not have x. So can we fix this simply by dividing all terms by e to the 2x? Yes, I think that will work. So let's do that. We're gonna divide this term by e to the 2x, and this term by e to the 2x, and this term by e to the 2x. And I think that has now taken care of the issue. We have now separated the variables appropriately because there is no y in here, there is no y in here, and there is no x here. So we're ready to integrate. We'll be able to integrate this one, the integral of the number 1 with respect to y. Hopefully you're aware of what that would be. But here, we should simplify this first. And same thing here. So we're going to rewrite this line now. So here's the key for this second term. This is just division of powers with the same base. The base happens to be the number e. But when you divide powers of the same base, what do you do with the exponents? You subtract them. So here, the new exponent is x minus 2x. And x minus 2x is negative x. Okay, it's 1x minus 2x, so it's negative 1x. All right, so that now is something we can integrate. And here, you don't integrate when the variable is in the denominator. The one exception to that, of course, is when the variable's in the denominator and has an exponent of a 1, right? Because that's the natural logarithm. But certainly this exponent is not 1. So we have to rewrite this using a negative exponent, just like that. And now we're all set. We're going to write the integral of each term, moving left to right. What's the integral of the number 1 with respect to y? Well, that is y. And now we have to remember the integral of exponential functions. They're pretty straightforward. All you do is repeat the exponential function, but in front of that, you're going to have 1 over the derivative of the exponent. So what's the derivative of negative 1x? It is negative 1. So a negative 1 will be there. And now we're here at the equal sign. And we have 4. And now we're integrating e to the negative 2x. So 4 is multiplied by the integral of e to the negative 2x. How do we integrate it? We simply repeat the exponential. But then in front of that, again, is 1 over the derivative of the exponent. What's the derivative of negative 2x? It's negative 2. Okay, and then here, I'm going to have my plus c. Okay, so what is this now? It's y. So 1 divided by negative 1 is just negative 1. So we get y plus negative e to the negative x, or y minus e to the negative x. And here, 4 times negative a half, well, this is just the same as 4 divided by negative 2. So we'll have negative 2 e to the negative 2x. And then this plus c. Okay, and that's perfect, just like that. And sometimes when it's very easy to do, like in this case, sometimes in the textbook answers, they would isolate y here, just so that it's in this form. Y equals, so basically this term goes to the right side where it will be positive. So we'll have e to the negative x minus 2e to the negative 2x plus c as another possible answer for problem 16. Okay, so again, when integrating the exponential function, you just repeat the function itself, but you divide by the derivative of the exponent. And of course, instead, if you are taking the derivative of an exponential function, you would multiply by the derivative of the exponent. All right, so that's problem 16. Let's do one more together. So I've selected this one as our final example for today. 28. Cos squared theta plus y cosecant theta times dy by d theta is 0. Okay, so let's go through the analysis here. I would say there are two non-zero terms. Two non-zero terms. The first thing is the differential cannot remain here in the denominator. So we start by multiplying the terms by d theta. So that will look like this. Cos squared theta times d theta plus y cosecant theta dy is 0. This remains 0 because even multiplying 0 by d theta would not change it. Okay, now we look at our terms. Any problem here? No, there is no y in that term. Is there a problem here? Absolutely. There should not be a theta in this term. This term has the differential dy. We cannot have the other variable theta in that term. Okay, so the independent variable is theta and the dependent variable is y. So how can we solve the problem here? Well, we can divide the terms by cosecant theta. Okay, so that's the plan. We're going to divide these terms, also 0, by cosecant theta, but of course it will stay 0. So let's do that. We're dividing the two terms here by cosecant theta. So how does that appear? That would look just like this. And that's perfect. The variables have been separated successfully, right? No problem here. No problem here. Okay? There are no thetas kicking around here, and there are no y's in here. So we're in good shape, assuming we know how to integrate these things. So this one should be easy enough to integrate. We're integrating y with respect to y. That means integrating y to the 1 with respect to y. So that's the most basic integral rule. What about this guy? A little more challenging, certainly. Maybe we'll play around with this a little bit. This is the same as cos squared theta times 1 over cosecant theta. But 1 over cosecant theta, you should recognize as something more basic. The identities included in the inside cover of your textbook. Look at this one. What is 1 over cosecant theta? It's the sine of theta. So we can write this instead, cos squared theta times the sine of theta d theta. That's better already. It's always better to use a main trig function where possible. One more thing. This business about cos squared theta, I'm hoping you remember what is actually squared here. We certainly talked about that a lot in our previous math courses. It means the whole cosine of theta is squared. All right, so that might help us as well with the integration. So I'm going to come to the bottom of the page. We're going to integrate this now using, yes, you guessed it, a u substitution. Okay, so here we go, down here. Let's set this up. So all you have to do is remember what to call u in this case. So the options are limited. Either u is the cosine of theta, or u is the sine of theta. I guess you might consider u is this whole thing, cos theta all squared, but we've never ever done that. It's like one of those power functions. So you always call the thing inside the bracket here your u. So u is cos theta. So then what is du? We need to know what the derivative of cos theta is. And that will go there with, of course, a d theta stuck to it. So the derivative of cos theta, you might remember it, but if you don't, we should be able to find it here. Okay, again, from the inside of your textbooks, the derivative of cos theta is negative sine theta. Negative sine theta. Okay, so we have u is cos theta, du is negative sine theta d theta. So we're going to rewrite this as the integral of u squared. Now, sine theta d theta is here. This is negative sine theta d theta. So this isn't exactly du. It's the negative of du. In other words, it's du multiplied by a -1, right? If you compare them, this is not exactly du. It is -1 times du. So that -1 factor can go here. All right, so this is similar to, I was thinking I'd show you, right? So this is from yesterday's video, problem 14, but just come to the bottom here. See, a very similar example. Doesn't look anything like the one we're doing, certainly, because there's no trigonometry, but look what we did. We said, call the inside of the bracket u. Its derivative is 8x dx. Over here, we had x dx, not 8x dx. So that means we had 1/8 of the du, and the 1/8 went out front. And we put in the du. This was u to the -1/2. Okay? Well, I'm saying that this is virtually the same thing. Here's the u squared. This isn't equal to du. It is equal to -1 times du. So the -1 factor comes out front. Then we have u squared du. Okay? So, you know, just wanted to remind you of that from yesterday. And okay, so now we can continue. So now we can actually take that -1 and multiply it by the integral of u squared du. How do you integrate u squared? Well, you certainly know how to do this. You add 1 to the exponent, and in front of that will be 1 over that exponent. Okay, and of course there'll be a constant. So this is -1/3 u cubed plus c. But don't leave the u there. Certainly we have to put back cosine of theta. So we get -1/3 cos theta all cubed plus c. And so that's what goes right here. negative 1/3 cos theta all cubed. The plus c, I'll just remember be putting in one constant for the whole equation. So this is now correctly integrated. Now we're here at the plus sign. And so what do? We integrate y. And remember, it's the same as y to the 1. So how do we integrate it? All we do is add 1 to the exponent. In front of that will be 1 over the new exponent. And here's where we'd put in the 1 constant for the whole equation. Okay? And I'm just going to temporarily call that C1 because I can see that it would be nice to clear out these fractions now, these fractional coefficients, by multiplying all 3 of these terms by 6. Okay, or actually even maybe nicer to multiply them all by -6. So I'll do that. So I'm going to multiply right here by -6. So that'll be +2. Right here we're going to multiply by -6. So that'll be -3. And here we would have -6 times C1, which can just be the new constant called C. So I'm going to write here, C is just -6 times the original C1. And that problem is now solved as well. Okay? Oh, and, I could have rewritten this cos cubed theta. So here's another option if you prefer. Cos cubed theta, like that, -3y squared is C. All right, but as far as I'm concerned, these are both beautiful final answers for that problem. Okay, so please make sure that you're working through some of the odd numbered problems from the exercise on your own. I have posted the solutions to accompany chapter 31 that the publisher has provided. So you can find those Washington textbook solutions posted for you, which hopefully will help you as you're working through some of these problems. In the next video, we are going to look at how you can find a particular solution. These solutions we've been finding are called general solutions because they involve the unknown constant C, right? All of the questions we've been doing involve this unspecified constant C. So these are called general solutions. And in the next video, we're going to look at how can you find a particular solution? So how, in other words, can we solve for C? And the short answer is we have to be given some information, some additional information in order to determine the variable C. So please work on some of this and then when you're ready, there will be, I guess towards the end of this week, a video, a third video on finding a particular solution using the separation of variables method. Okay, thanks a lot, guys. I hope you're all doing well. Have a great day.